Hello, in this video I want to introduce the, the Markov switching model as the first part of a workshop that I have presented at Qatar University in advanced econometrics using Eviews software. First of all, I want to present the importance of structure break in general. Then specifically I want to present the Markov switching model, how to simulate a Markov switching model. Then I want to present the Hamilton 1989 GMP example. After that, the Kim and Nilsson 1999 example about returns volatility. Quickly, as you know, macroeconomics and financial variables are subject to several shocks that create breaks inside these time series, and in general we use we can use different model to capture this switching. We can use the structural change model proposed by and Peron 1998 and 2003. We can use also a class of model known by TAR model, threshold autoregressive model, introduced by Tong 1980, and also we can use the Markov switching model proposed and developed in 1989 by James Hamilton. Okay, concerning the date of breaks, in general these dates correspond to some economic and financial and international events such as economic recession, economic expansion, turning points in economic cycle, etc. Also, this date of breaks can correspond to financial crisis, and sometimes we need to estimate this break before to divide our sample or our period in period before and after crisis, or before, during, and after crisis. We can use also break to for time varying volatility, which means that we can model, for example, returns using a Markov switching model with only switch in the variance sigma 1, sigma 2, sigma 3, and in this case, for example, sigma 1 corresponds to low, sigma 2 to medium, and sigma 3 corresponds to high volatility, sigma 1 lower than sigma 2 and sigma 2 lower than sigma 3. Also, we can use this model to break date, or this break date can correspond to political tensions, wars, etc. Okay, the presence of break can create some problems, such as in many cases, we cannot use tests such as likelihood ratio, LM, and Wald test to test between linear and non-linear, for example, between linear model and Markov switching with two states. And in this case, why? Because in this case, there are some parameters that are not identified under the Banach hypothesis, and we call this nuisance parameters. For example, P11 and P22 under the Markov switching model, and the delay parameter D, and the threshold parameter C under the threshold autoregressive star model, etc. Also, neglecting breaks creates some problem of misspecification, and in general, the presence of breaks can create some problems like spurious long memory, and interested in this subject can see the paper of Diebold and Inoue 2001 and many other papers published in this period. Okay, in general, we can detect structural change in stationary, non-stationary, and also on co-integration relationship. The difference is that for the first case, structural break, if the time series is stationary, in this case we can use model that account for structural breaks for modeling both the mean, and in general we use this for macroeconomic variables, and the variance in general for financial data. And the model that we can use under this first category, we can use the Hamilton 1989. Also, we can use, for example, the Swash model proposed by Hamilton and Sismel 1994. When testing for unit root, especially the second category is when testing for unit root, especially in macroeconomic data, a possible non-rejection or of the unit root hypothesis can be due to the existence of breaks, structural breaks, and we can, interested in this topic, can see the paper of Piron 1989, Zifot and Unfu 1992, Patinos 2005, and Sylvester et al. 2009. And the third category is when we are interested by testing for breaks in co-integration, and in this case we can see the paper of Grigory and Einstein, Arai and Korozumi 2007, the paper of Hatimi G 2009, Tijurol and Piron 2008-2010. Okay. Now for the class of model with structure break, we consider three kinds of model. The first class of model is the Markov switching model, where the switch from one regime to another one is governed by unobserved Markov chain. The second class that I will to present in another video, it concerns the class of structural change model by Piron 1998 and 2003. And here the switch from one regime to another one is governed by the time. In the first one, it is governed by unobserved Markov chain, first order Markov chain. Here it's governed by the time. But and for the third class, the threshold autoregressive model, which is proposed by Tong in 1980. And here the switch from one regime to another one is governed by the lag dependent variable yt minus d, and yt is the dependent variable in general, but there are many other extensions. And the threshold parameter is C. Now we focus in the first class of model, which is the Markov switching model. This model has been proposed for the first time by Hamilton 1989, and in the paper a new approach to the economic analysis of non-stationary time series and the business cycle. This paper is have been cited more than 6,821. Okay, and it has been used in many research articles. The advantage of this model is that this model can be used to model change in mean and in variance. Also, this model can allow for multiple breaks, and also this model can detect outliers inside time series. The first example, here I have estimated Markov switching model in the US inflation rate, and here I have detected many breaks. Okay, the first one corresponds to the Vietnam War. Here, 67, May 67, and the second one, it is corresponds to the first oil shocks, the beginning of the first oil shocks, which corresponds to the date June 73, and here the second break corresponds to January 75, the end of the first oil shock. Then here it is the beginning of the second oil shock, at the end of the second oil shock, etc. Here it's, I think it's the war, the Gulf War, okay, etc. We continue. How I have detected this break? I used the probability smoothing for, which is estimated when we use the Markov switching model. We use the probability smoothing to determine the date of break, and in general, following Hamilton 1989, when the probability of smoothing is bigger than 0.5, in this case we have switches between the first result to the second one. For example, if P11 is we move now to the mathematical presentation of this model. The general form of this model is given by this equation, where mu st is the mean of our model, the mean of our series, okay, and here the error is normally distributed with mean 0, and the variance is sigma square st, okay, where mu st is given by mu1 s1t plus mu smt, and also same thing for sigma square st. It is given by this quantity, where smt is equal to 1 for the first region, and when st is equal to m for the m region number m, and 0 otherwise, which means that, for example, if s1t is equal to 1, this means that we are in the first region, and for all the other from m equal to capital M are equal to 0, which means that we have mu st is equal to mu1, and sigma square st is equal to sigma 1 square. And in this case, we are in the first region with mean mu1, and the variance is sigma 1 square, and so on. Okay, for the probability Ps equal to G given to St minus 1 equal to I is equal to Pig. This is the probability of switching from the regime I to the regime G, which means that at t minus 1 we are in region I, and we switch to region G. Suppose that we have now St is equal to I, St minus 1 is equal to I also. In this case, we have this probability is equal to Pii, and it means that at t minus 1 we are in region I, and we stay in the same region at t. Okay. Some characteristic of this model, we can when we estimate the model, we can get the probability and the filtered and smoothed probabilities, and in general we use the smoothed probability to detect breaks. Yeah, if P11 is bigger than 0.5, it means that if P12 is bigger than 0.5, in this case we switch from one region to another one. It is P12. Okay. Then the second characteristic or feature of this model is the expected duration of each region. This is very important. Why? Because in general, when dealing with Markov switching model, the most important question is, given that we are actually in regime G, for example, high volatility, how long on average we will stay in this region, or will this region last? Okay, the expected duration is given by this formula. Expected duration is equal to 1 over 1 minus PGG, And for the first regime, it is given by this one, and for the second regime, it is given by 1 over 1 minus p to 2. Okay, there are some problems. One, testing between one regime or linear model, linear model against the alternative of two of Markov switching with two regimes. In this case, the LR, light load ratio, LN, and volt tests does not have their standard distribution, and we cannot use the usual distribution, the usual test to test between linear against the alternative of two state Markov switching model. Many others have developed some theory to resolve this problem, and just quickly we can, those who are interested in this model can look to the paper of David 1977, Bruce Hansen 1992, or René Garcia 1998. Okay, we start by a simple example, okay, with a Markov switching model without autoregressive lags, okay, and here we have mu t is equal to mu s t plus epsilon t, and we suppose that epsilon t, okay, here is normally distributed with variance sigma square st. In this case, mu st is equal to this mu1 s1t plus mu2 s2t, and sigma square st is equal to sigma square sigma 1 square s1t plus sigma 2 square s2t, and here sum of the probability here is equal to 1. S1t is equal to 1 if st is equal to 1, and s1t equal to 0 otherwise. Okay, we start by the first example here, where yt is equal to minus 1 plus 1. 1 is sigma 1, and minus 1 is mu 1 time ut, which is normally distributed with mean 0 and variance 1. And we suppose here that P00 is equal to 90,099, the 00 for the first regime, and P11 for the second regime. Sometimes we say P00, P11, or P11, P22, it's the same. Okay, P11 is equal to 0.98, and here we have the mean is 3, and the standard error is equal to 2, which means that the variance is equal to 4 here, and the variance is equal to 1 here, 1 square, 2 square. Okay, we can, okay, in the trajectory we see that we have switch two regimes. The first one is here, okay, this one, and the second one is here, okay, this one is the second, okay. For the first one, it is about minus 1, okay, in general it is about minus 1, and this one it is about 3. If you look here, it's about 3, okay, the mean is about 3, and you can see also that the volatility of the second of this one is higher than the volatility of this one, the variability about the mean. Okay, just to see this is a trajectory of this simulated model. We go now to our data. This is simulated using Gauss software. This is our data. Okay, we can, this is here, we can go to graph, and then we can plot the trajectory of this time series, and to estimate this model, okay, from view, okay, excuse me, we plot this, we go to quick estimate equation, and we write ms, and suppose we select the method which is switching at the end, okay, and here ms, and it is followed by the list of switching regressors. We consider here that we have only C, okay, the constant that we switch we want to replicate the same result, okay? And suppose that we don't have a non-switching regressor. If you want to select here mean that C switch, the mean switch from two regimes, okay? We want to select here after that Markov, two regimes, and here we can, if we select this one, it means that not only the mean which switch from one regime to another one, following the Markov first Markov chain, but also the error variance switch from one regime to another one. Okay. Here, why I have selected this one, because in our model we have in this simulated data we have both the mean and the variance which switch from one region to another one. Okay, we have selected Markov here, and here we have the number of regimes. We go to options sometimes here. As you know, this is a non-linear model, and in this case we need starting value, and sometimes we should re-estimate many times this model to get a consistent estimate of the coefficients. Okay, we click OK now, and now it is running, and here we have, okay, this is the estimation of our model. This is the mu of the first region, -1, and if you look here, it is -1. Also, the C, it is equal to 3, and here also we have the C of the second, the mean of the second region is equal to 3. For the first region, as you know, the standard deviation is equal or equal to 1, and 2 in the second region. Okay, for the first one, it is equal to, this is equal to 0.017, but it is the logarithm. If we take the exponential, you know that exponential it is about 0, and exponential of 0 is about 1. Okay, and also for this one, the exponential of 0.69, you can go to Gauss, for example, and here, and we can verify this result quickly if you want. Okay, and it is very easy. The exponential of 0.017, and it is equal to 1. Okay, and same thing for the second one, the exponential of 0.6927, and it is about 2, and here it is equal to 2. Okay, this, as you can see, the first one is significant, this one is significant, this one is significant, but the second, the first variance is standard deviation is not significant. Okay, also we can go, if you want to see the estimated probability, the matrix probability, we can go to, okay, view. After estimating the model, you go to view region results, you go to transitions, and here you select summarize, and okay, and here you have the estimated probability. It is about 0.988. Okay, it is 0.99. Okay, and here 0.98. It is for the second 0.98. It's approximately equal. Okay, and also we have the expected duration, which is equal to 88.29 and 61.02. We can verify this result using the rule that I have proposed, I have presented to you. 1 minus P11, this one, okay, this one, P11, and we get this result, okay, 0.99, and we divide, and it is equal to, sorry, just we add the last part, 674, okay, I remove this, and it is equal to 88, okay, and second one if you want. It is equal to 1 minus 0.6102414, and we get the same result. It is, excuse me, 1 minus 0, excuse me, it's not this one. It is 0, sorry, 0.983613, and it's okay. And here you have 61. Okay, we have verified this. If you want to get the probability smoothing, you go to regime results. Okay, regime probability. You select this one, and here you can select the one step ahead, filtered probability, smoothed probability. You can select also for single graph in the same graph, for multiple graphs. Okay, I select multiple graphs and smoothed probability. Okay, and here you have this probability. Okay, as you can see here, this one, this first part corresponds to regime with -2. Okay, it is this one here. And for just some few observations, we remove to the second. Okay, we remove this one. And then we stay in this regime many times. It is here, this one, okay. And then we remove another one, and this corresponds to this one, this few observations. And here, why we stay more? Because we use 0.99, which means that we stay more. You know that the expected duration is 1 minus 0.99, and this means that we stay more in this region in average, okay, because we divide by 1 minus 0.99, and okay, this period, it corresponds to for the first regime with for the second regime, excuse me, with mean 3, and it is it corresponds to this one. Okay, it corresponds to etc. Okay, if you want, for example, to see the filtered probability, it's the same thing. You go to filter, and okay, this is the filtered probability. It is not the same, but it's approximately the same thing than the smoothed probability. For residual, if you select here, you go, this is the regime. Okay, this is the regime, and the date of breaks corresponds to this date. Okay, and you can use the probability. You go to here, actual fitted residual table, and here you have the fitted. This is the fitted residual, etc. And also, if you want residual graph, etc. Okay. If you want now, we can move to another example, okay, which is the example of Hamilton. '89, and here we click to this one. We go back to these are the estimations that I have reported. Okay, and now this is the model proposed by Hamilton 1989, and here he considered a Markov switching with only switching in the mean but not in the variance, and also he supposed that the GMP switch from two regimes, and here we suppose that mu st is equal to mu 01 minus st plus mu 1 st. If st is equal to 1, in this case we have mu 1, and if st equal to 0, we have mu 0. And here this is the time series, the growth, okay, this is the growth rate, and this is the time, the trajectory, and to estimate the Markov switching, we go to we estimate equation, we select Markov switching, and then we can select here G, okay, C, and for the non-switching regressor, we don't have here, we select G minus 1, G minus 2, G minus 3, G minus 4, okay, and we select Markov 2 and okay, and here you have the result, okay, or for the first and the second regime, or we have here the result, okay, it is the same here. If excuse me, here for this one, if this coefficient switch Phi1, Phi2, Phi3, but for the Markov switching, these coefficients are not does not switch from one region to another one. In this case, we take this one, okay, and here, and we select and okay, and this is the result, okay, the result of our estimation. It is equal to this one, which is I have reported here in the document. Here it is equal to this one, okay. We take because it is autoregressive, okay. AR1, AR2, AR3, AR autoregressive 4, and here you can compare this result with the result obtained by in Hamilton 1989, okay. Just I repeat, G, C, which is the mean, which switch from one region to another one, and then we have used AR1, AR2, AR3, and 4. We select Markov switching, okay. We don't select this one because we suppose here that the error does not switch from one region to another one, and here we don't change, modify anything, and we select okay. Just one remark is that sometimes when you estimate the model here, you cannot get the result. We cannot converge to the result. We don't have a convergence, and in this case, we should remove this starting value, and we estimate another one. Sometimes it takes more than 2 or 3 minutes to estimate the model to get the result, and it is important to do this many times to get a consistent result, and you can compare your estimation from the first one and the second by comparing the log-likelihood ratio. And those who are interested in testing between linear and two-state, and two-state against three-state, three-state against four-state, they can go to the papers of Davies, Bruce and also the paper of René Garcia. Okay, now just quickly, I want to show you this is the result. Okay. Okay, we go now to the last example, which is which replicate the result of Kim and Nilsson 1999, where we estimate a Markov switching model with a three-state Markov switching model of in the stock returns from 1926 to 1986, and here because we want to model the stock returns, and as you know, stock returns are characterized by switching in the variance and not in the mean. I think it's reported here. Okay, it's not a problem. I go to this example, Kim and Nilsson, estimate, and here you can see these are the x's. This is the time series, and when you use here, we see that we have high volatility here, also here, okay, and here we have small volatility, okay, and here it is medium volatility. It means that we have an idea from the trajectory of the time series, and we want to estimate a Markov switching model, okay. You have, if we see to the mean, we have the mean is about 0. We don't have switching in the mean, but in the variance, we go for this series to view, okay, or it is here. It is estimated here, I think. It's not a problem. Okay, estimate. You go to quick, okay. You go to quick, if you want. Estimate equation. You go to class 1, and then you go to your excess, and here we don't write C because we don't, the mean does not change over time, and but yes, we select regime specific error variance, and here we select Markov and 3 as suggested by Kim and Nelson, and we estimate the model. Okay, this is very important. Here we don't get, we don't have warning, singular covariance, coefficients are not unique. We should estimate many times, this model. Okay, we go to option, we remove this, and we estimate another one. And now we have the coefficients are significant, okay, are significant. We can compare our result to these obtained by Kim. Okay, I think here just quickly, and here we have the result. It is the same, okay, the same coefficient. This one is this one, and this one is this one. Okay, and now here you have the coefficient, okay, the coefficient or the coefficient of estimated variance sigma are significant. We go to regimes, transition, summary, and here we have the probability, which is close to 1. You know that when the probability is close to 1, it means that we stay more in our regime. And in general, for the Markov switching model to be significant, this probability should be close to 1. Not equal to 1, but close. And here you have how many times more these probabilities are close to 1, more we stay in this regime, and this, for example, here 0.97, we stay 37. 37 what? 37. If your data is monthly, it means that we stay 37 more. If your data is weekly, 37 weeks. Okay, here it's about 38. And here 0.96, it is lower than P11, and which means that we stay less. It is 31 or about 32, and same thing here, it is less than P22, which means that we stay less than 32, and here we stay 20, I think 20, if I remember, 20 months, okay, which means about 2 years less 4 months. Okay. What else? Okay, we can go also to the probability, smoothing, view, regime probability, and we select this one, and here you have the probability smoothing. This is for the first regime, second regime, and third regime, and we can compare the result with the trajectory if you want. Okay, here quickly, just to have an idea about this. Okay, and we select, this is the excess region, this one, excuse me, and if you take it and here, okay, this is the first period where we have this one, these two regimes, okay, this one and this one, this small period. The first is when we have low volatility, it's corresponding to this one, and this region corresponds to this period also, which corresponds to this one. Okay, for this one and this one, they correspond to the third regime with high volatility. High volatility. This one, it is repeated here also. And for the medium volatility, it corresponds to all these periods. This one, okay, this period here, okay, and also here, this one and this one, which correspond to this and this. And at the end, we return to come back to region 1 here. Okay, I think it's I have give you the most important feature of this model. I think I don't have something else to add. Okay, thank you very much. And I hope that it is this presentation can help you to understand this model.